All right. Wow. Hello, everyone. Welcome back to Comp 2150, Object Orientation. I don't know about you, but I am really looking forward to that reading week break. Yeah, I'm really looking forward to that. Today, what I would like us to do is finish up with this method redefinition stuff. I want to take the time to step through that Java code that I showed you at the end of last class, because it was a bit of a feverish, like, let's click run and wow, there's output and I don't really know what's quite going on. So let's step through it and make sure that we're all on the same page about what's happening in terms of how instance variables in Java are shadowed. And then what I'd like to do is spend some time taking a look at the relationship between Java and C++ in this regard. So how is shadowing applying to different parts of what C++ is doing compared to what Java is doing? After that, the thing that we're going to take a look at is something called the Orthodox Canonical Class Form, OCCF, Orthodox Canonical, I can't even say it all, canonical, OCCF, let's just call it OCCF. We're going to take a look at OCCF, and what OCCF is, really broadly, is just, these are the methods that you should define for classes in languages like C++. There are specific sets of methods that you should define. We are going to focus entirely on destructors today. So there's 4 different kinds of methods that you should call or create in this approach. We're going to specifically be talking about destructors, and we're explicitly talking about destructors because it's required for you to do this for your assignment. You have to use destructors in assignment 2. The other things that are part of OCCF, copy constructors, and then overloading the assignment operator is not required for assignment 2, but using a destructor is. So we'll take a look at building destructors for our classes in C++. All right, so let's talk about shadowing. In Java, we have this situation where for methods, polymorphism is just always on. We have classes and subclasses. We call a method on a static type, and the correct method is going to be invoked. So we have polymorphism always on in Java. We can shadow instance variables. So we can have 2 classes that are related hierarchically. One extends the other. They can both have instance variables that have identical names. And having these identically named instance variables then is shadowing. We're going to have the value that we get for the instance variable that we're referring to depends on the static type of the variable that we're operating on. What we're going to see is that in C++, shadowing is also possible for methods. This was something that when we began to look at C++ and we started to look at that virtual keyword, we kind of just blindly said you almost certainly always want to use virtual, and that's still true. That's still true. But what are the unintended consequences if you don't use the virtual keyword? So let's take a look at shadowing methods in C++. This was the code fragment that I showed you as kind of a starting point. Let's take a look at that code fragment again in Java here in VS Code. And I'm going to run it, and I kind of want to step through what's happening in this code fragment as we're going through it. So on lines 4 and 5 here, we're declaring and initializing 2 variables. One of them is called P and one of them is called C. We're creating instances of these 2 classes that are related to each other hierarchically. And I'll remind you quickly, parent has this public int value. It's an integer. And we have a method on this that's called method. The child class also has public int value, and it also has a void method called method. In main, we're creating instances of these variables. And then we're printing out the instance variables that are assigned to those instances of classes when they're constructed. So on line 8, we're printing this line out. P.value is equal to 37. That makes sense. We just created an instance of this parent class. And in the constructor for the parent class, we're setting value to be 37. That completely makes sense. There's nothing weird about that. That's just what we would have expected to get as output here. On line 9, we're printing out child's value. And child.value here, when it was constructed, was assigned the value of 7. Again, there's nothing weird here. This is just normal behavior. This is what I would have expected to see as output. We call methods on those, and the methods that we've defined in these classes are doing kind of what we're expecting them to do. So if I call p.method, I'm invoking the parent's method. If I call c.method, I'm invoking the child's method, and we get the appropriate output here. Line 15 here is where we do something that's unexpected. Now we're starting to change the setup here. On line 15, we're assigning whatever c is to p. So the value that we're binding to p is whatever the value is that c has, and c is an instance of that class child. That means that p and c as objects, they should be identical now. They are the same thing. We're just assigning, we're replacing one with the other. So they should be identical. When I print out p.value here, what I get as output here is still 37. I've replaced this class with its subclass. I've replaced it. So I said p is equal to an instance of child. The value that child has for value is 7. This is unexpected. The output that we're seeing here is unexpected because the actual type that this thing has at runtime is of type child. But because these value variables are shadowed, they have the same type, they have the same name, we're looking up which value variable, which instance variable we're referring to by the static type of the variable that we're interacting with. So even though p and c are identical after this line, we're still getting this value 37 being printed out because the static type of p is parent. And so we're kind of using that class's instance variable to print out this value. C.value is still the same thing that we would expect because we haven't changed what c is. So we're saying c.value is 7. And then when we call p.method and c.method, in both cases here, we're invoking the method in the child class. So again, we've replaced the value of what p had with an instance of c. So we're calling that method on the child class. And we're calling that method on the child class in both cases here now. Yeah.
Child value is changed, or is it that we're looking into the parent class value?
So I'm going to try and restate it, and then I'll ask if I've answered your question, just to make sure that we're talking about the same thing. When we're invoking methods here, we're looking at the dynamic class, the dynamic binding for what this value happens to be, and then we're doing that whole message to method mapping lookup. So based on the type that this has at runtime, which method should we be invoking? And that's going to give us, in both cases here, child. We're calling that child method. For this part, where we're printing out p.value and c.value, these are being shadowed. They're shadowing each other. So we're going to be using the static type of the variable itself to decide which one of the values we're trying to use. The child class, as an extension of parent, it has both. It has both value from parent and value from itself, but they're two separate variables. We can still refer to the parent one by casting it to that type parent and getting that value printed out. So C itself, the child instance itself, it has an instance of both variables. The parent class doesn't know anything about child because it doesn't get to set. When we create an instance of parent up here on line 4, it only has 37.
So we never get it.
We could never get 7 from that because the parent class, as it's defined, it doesn't really know anything about things that extend it. Yeah, but the child class, because it extends parent, it's getting copy of whatever the parent class has. Does that answer your question? Okay, good. Any other questions about this? Weird. It's kind of weird. Okay. So in Java, we can shadow instance variables. And we're referring to instance variables by the static type that the variable has. We cannot shadow methods just because in Java, polymorphism is just always on and we cannot turn it off. We get this by default. We cannot change, we can't change the behavior of that in Java. In C++, though, we actually can have shadowed methods. So we can have methods that have the exact same signature in 2 classes that are related to each other hierarchically. And then using the static type of the variable that we're referring to, the static type that is the class that we're referring to, it will invoke different methods based on that. In a similar way to what we just saw with instance variables in Java. Let's take a look at the item hierarchy that we had before. So I'm going to close this whole Java setup, and I'm going to open up item.h here. This is the thing that we were working on originally to get some class hierarchy stuff going on in C++, in that we hadn't seen it before. And what I've added to this is a new method that's called print. We made item as a class abstract by having this pure virtual method in it. So we did this virtual and then assign equals 0 to the method, and that makes this method abstract, and thus it makes the class itself abstract. But despite being abstract, we can still have methods that are not abstract in a class. We can still have non-abstract methods in this class. So I've got this print method, and then the subclass of item was potion. And I've created another method in potion that has the exact same signature as the print function or the print methods that's defined in the item class. So we've got these 2 methods. There's print in the parent item class, and there's print in the child potion class. The parent class has not marked this as a virtual method. It hasn't marked it as a virtual method, and it hasn't marked it as a pure virtual method. It's just a method on the class item, and that's it. I am going to open up item.cpp, and all this method does for now is it just prints out, I'm in the superclass, and the type of it is something. And I'm going to take a look at potion.cpp, and the only thing that potion's print method does is just print out that I'm in the subclass. So I just want to really easily visually see the difference between which method I'm calling at runtime. Yes?
In that potion class, can you see the type that's been passed to the constructor?
So here,
Yeah, can you actually
the only way we would be able to get access to that is to provide an accessor for that in the superclass, because it's private. If we marked it protected, then we would be able to see it. But because it's private, we can't see it. Make sense? Good, good. Okay, so the main difference between the print method in potion and the print method in item is that I'm just printing out different messages so that when I'm printing stuff, when I'm calling these methods, I can really clearly see the difference between the 2 of them. I've also then written this test item.cpp file. So this just has a main function, and I'm just using this to create instances of these classes and to invoke methods on those instances. I'm going to compile this, and I'm going to run it. And then I'm going to step through this in the same kind of way that I just did with the Java one, just to see what's happening at runtime as this thing is running. So I'm going to run make. I have a make file in here. It's the same make file that you've seen a few times. I've just added a couple of Java files in there. I'm going to do something a little different. I'm going to say make, and then I'm going to say -j and 10. This is a total aside. This is not related to the course at all. Make is a build system. It's not a C or C++ building system. It's just it's a dependency solving tool. That's all it does, is you tell it what the dependencies are, and here are the commands to solve those dependencies. Make has this really nice feature called a job server, where it can run builds in parallel. And so make J10 says, use 10 processors to build these things in parallel. And then it builds up the graph of dependencies, and then it goes and solves all that so that you can run these different subparts of it in parallel. Total tangent, not really helpful to the course. I've abused this feature personally to convert my FLAC audio library to MP3 and take advantage of all the processors on my laptop. But yeah, I'm just a kind of a nerd, so. Okay, so I've written this test item file. This is my program called test item. On line 9, we're creating a variable called x. It is a pointer to item. Its static type is pointer to item. Because item, is an abstract class, we can't make a stack variable. This is forbidden. We can't do this because we can only have instances of subtypes of this class. I can make a pointer to item because it's an abstract class, but I can't do stack allocated variables for abstract classes. So on line 8, I create this instance, I create this variable called item by, called x. It is a static type of item pointer. On line 10, I assign it to an instance of the subtype potion. And then on line 12, I'm calling print. I'm calling the print method on this instance. I'm actually going to comment these lines out here. And I'm going to make it again, and I'm going to run test item. So the method print in this hierarchy that we have of item and potion is shadowed. When we call x print, so x arrow print, what we're referring to is the method in item.cpp and that's the one that's being invoked. We're looking at the method that's defined in the static type of the variable. It hasn't been marked as virtual in the superclass. Because it hasn't been marked as virtual in the superclass, the method that gets invoked is the one that is defined in the static type of the variable that we're calling the method on. If I uncomment these lines now, on line 14, I'm making a pointer to potion, and the variable is called p. So the static type of p is pointer to potion. Here I'm using that dynamic cast method. Remember, there's no instance of in C++. This is the option that we've got, is cast it to a lower type. I want to cast this instance x to potion pointer. It's a potion. That's what I created in the first place. So I'm going to cast it. I have to check to see if it's not a null pointer. This is what tells me this is not an instance of that class. If that was null, it would not be an instance of that class. And now I'm going to call the print method on p. So effectively what I've done is I've taken this object that I created and I've cast it down so that the static type of it is potion. I'm going to compile this again, and I'm going to run it. The second time we run this, the method that gets invoked is the one in the subclass. So the behavior here is kind of identical to the way that that instance variables in Java was working. In Java, when we have shadowed instance variables, it's the static type of the variable that we're looking at that defines which instance variable we're referring to. In C++, we can have shadowed methods, and it depends on the instance type, the static type of the instance that we're referring to that says which of those methods are going to be invoked. This is a really quite a long-winded way of saying if your intent is to have methods be overridden, to use polymorphism in C++, mark the methods as virtual. So if I say here that this is a virtual void print, I'm saying you should be allowed to override these things. I'm going to make this again. Oh, nothing is done for all, so I'm going to make clean. I'm getting a bunch of warnings here. The warnings here are saying the print method overrides another one, but it's not marked override. Okay, well, that's actually quite helpful. Thank you. If you want to use, if you want polymorphism to happen here, you have to explicitly go through this process of saying virtual and override. So if I test item again, it's both going to be in the subtype this time because we've turned polymorphism on. I'm going to turn it back off just to keep that example showing the same behavior. C++ is, it's there. Yeah, it's there. C++, we're talking a lot about C++ in this course. And there's so much C++. There is just so much C++. There's stuff that we're not going to talk about in this course because if we just talked about that stuff in this course, we'd be here for, I don't know, probably an entire undergraduate degree just talking about C++. This is something that C++, I've said the joke before, C++ is C+1, but the reality is it's more like C+, I don't know, everything. C++ the kitchen sink. You know, the designers of C++ are just trying to get anything and everything into the language. The number of times where you'd want to use shadowed methods is like vanishingly small, but it's still part of the language and it's still there. So my advice again is always make sure that you're using the virtual keyword if you intend to use polymorphism in a hierarchy. All right. Any questions about that? Okay. Yeah.
Regarding the warning using the override keyword.
Yeah.
What happens if you? What would have happened if you did it right?
Well, let's check it out. Let's try it. It still works. It still behaves the same way. It's just telling us that you probably meant to do this. The override as a keyword wasn't always in C++. It's only been added. It's been added recently, 10 years ago. Any other questions? Okay. So here it is succinctly. This is what we're doing. The behavior is that the shadowed methods are called based on the static type of the variable that you're working with. I'm not going to code anything about this. I'm really just bringing it to your attention. In Java, you can forbid extension from a class by using the final keyword. You can forbid methods from being overridden and using the final keyword. You can do the same thing in C++. It's the exact same keyword and it's used in exactly the same way. If you don't want a method to be overridden in C++, you mark it final. If you don't want a class to be extended in C++, you mark it as final when you declare the class. The circumstances where you want to do this are when you very explicitly don't want to have a hierarchy of classes being built off of the thing that you are that you're doing. All right, so let's move on. What we were just talking about, shadowing, is one a topic related to redefining methods, so naming methods the same way across multiple types in a hierarchy. The other way that we can think about redefining methods is by using the same name for a method, but using different types in the argument or the parameter list for that method. Let's take a look at a couple of examples, and we're going to give names to these different examples. There's this idea of covariance, there's an idea of contravariance, and there's an idea of non-variance. And we'll look at each of these with an example. Here's the setup. I have a class hierarchy here. I've got a superclass, and the superclass is extended by something called subclass. Covariance is when you have parameters or return types to a method that use more specialized types in the subclass. So I've got subclass extends superclass. That's my setup here. Now I've got another type hierarchy, first and second. Second extends first. We've got methods in each of these classes that are named the same way. This is a Java example. Method 1 takes superclass in the superclass first. Method 1 takes subclass in the subclass second. The return types on method 2, same thing, superclass, subclass. So in the subclass, we are going to a more specialized version of the arguments that we're taking. This is defined as covariance. So it's a tighter version of what we're talking about. Contravariance is sort of the opposite here. Contravariance is that the return types and arguments to methods are less specialized types. So we've got first and second again. In second, now we have object as opposed to whatever the subtype was that we had previously defined. This is contravariance. Non-variance is another way of basically saying that when you've got these contravariant or covariant methods, these are actually different methods. They're different methods in Java. So Java is a non-variant language, and that means that these covariant or contravariant methods are actually just different methods, and when you call them, they are going to have, they're going to be called based on the type that you're actually passing. If you want to have something like the equals class, you have to use this. If you want to have something like equals and override what's defined in object, you have to use downcasting. You have to use downcasting an instance of in that bottom part of the class hierarchy that you want to use this with. Both Java and C++ allow covariant return types. So this actually behaves polymorphically the way that you'd expect it to. So really quickly, covariance, we've got methods that are redefined in subclasses. The redefined methods have tighter versions of the class parameter itself. Contravariance is the opposite. And non-variance, Java is a non-variant language, so these are just different methods. They're actually different methods. Okay, let's do something different. I want you to join this Mentimeter. So I'm going to leave this up here for just a second, and I'm going to show you the code separately, because I found when we did the Kahoot last time, the code was just like minuscule. And what I'm going to do is I'm going to get you to join this Mentimeter, and then I'm going to show you VS Code. I'm going to show you an example in VS Code, and then give you, like, I don't know, 30 or 45 seconds to answer the question. So I'll give you 30 seconds to join this, and then I'll switch over to the first code example. It's Java. It's Java. Okay, we're connected. Thumbs up. Okay. Here is the first example. So this won't compile because I'm missing stuff, but take 45 seconds, 30, 45 seconds, read this and try to decide what this is going to print out. Feel free to talk to your neighbor if you want. Okay, I'm going to pop over to Mentimeter again. I'll try to put them side by side here. So a lot of people are saying less super. Let's step through this. We've got super and less super. Less super extends super. And we have shadowing of this string item. So the super class has the same variable name and type as the subclass. We've got super s is equal to to a new less super. We're creating an instance of this, but the static type of the variable is super. So when we say s.item here, print out s.item, the item that we are referring to is the one in the superclass. The one in the superclass. So in this case, we're going to be getting super. Are we okay with that? We're okay with that? It's the static type. It's specifically the static type that we're referring to here that's making that distinction between the two of them. Okay, let's go to the next example. Put 30 seconds on my timer again. Okay, good, perfect, good, excellent. So because we're calling a method this time on line 23 here, we are getting polymorphic behavior. So because we're calling the method, we're getting polymorphic behavior. And because this is an instance of less super at runtime, we're referring to this print method. And that print method is referring to the item that's in its scope. So whichever item is inside that object is going to be the one that we get printed out. So great, excellent, good. Here's number 3. I'm going to put 45 seconds on my timer this time because there's a lot more code here. Please also feel free to talk to your neighbor. Okay. I'm delighted to hear you talking to each other about this. I'm delighted to hear you talking to each other about this. We're mixing two things here now. we're now mixing shadowing and polymorphism, and that whole idea of contravariance and covariance. We're mixing these ideas together now. I'm going to I'm intentionally not using the words covariance and contravariance in this description, just to prime you for the next question. We've got this variable called super, and we're assigning to it an instance of the subtype less super. We've got a variable called t, its static type is above, and we're assigning to it an instance of the subtype below. On this super method, or on this super object, we are calling the method print. The method print that we're going to be looking for matches the static type that this variable has. So the static type of t here is above. This is a different method. This is a different method from this one. These are two completely different methods that coincidentally have the same name. They accept different types of arguments. So the type that we actually are going to be using here is the one that has the method that accepts an input of the static type of above. This is the one that accepts the static type of above, and so we are printing out super. Print and print coincidentally have the same name and return type. They coincidentally have the same name and return type. They are different methods. They are completely different methods. Here's the next question. Java is a non-variant language. Yes, that's absolutely true. That is 100% true. Java is a non-variant language. When we're thinking about the relationship between this print and this print, it's going to be one of contra or covariant. It's going to be one of those two things. The superclass here has the super type as its argument. The subclass has the subtype as its argument. These are covariant methods. We have a more precise definition of the type that we have in the child class. And so this is a covariant example. We okay with that? Should I go back, step through covariance and contravariance again, or just keep moving? Thumbs up cannot convey any of those ideas. Let's take a look at this again. Let's take a look at this again. Covariance is where we've got parameters or return types in the subclass. So we've got this super and subclass relationship. We have two classes that are related to each other hierarchically. The two classes have methods that have the same name. They have the same name. So in first here, we've got method 1. In second, we've got method 2. The argument to method 1 in the superclass is of type superclass. So the argument itself has a type, and it's at the top of its own hierarchy. The argument here to method 1 in the subclass has a different type. The type that it has is a subtype of the type that's being passed to method 1 in the superclass. So within these arguments, let's ignore everything else right now. Just the arguments. Superclass is the superclass. Subclass is the subclass. This is a more precise class. It's lower in the hierarchy of classes between superclass and subclass. Method 1 in first and method 1 in second, they are related to each other because of the parent-child relationship. They coincidentally have the same name. And because the arguments to method 1 in the subclass are a more precise type than they are in the superclass, it's described as a covariant relationship between these two methods. Java is a non-variant language, so these are just fully two separate methods. The one that gets invoked depends on what we're passing to it. It's not going to behave polymorphically. So if we pass an instance of subclass to method 1, it's going to invoke the method on the subclass. If we pass an instance of superclass to method 1, it's going to invoke that method on the superclass and not the subclass. So very broadly and generally, this is a covariant relationship between these two classes and their method. But Java is a non-variant language. So those are just two separate methods. So it's almost as though their types are not necessarily related at all. Contravariance is the opposite. The subclass has a higher class in the hierarchy than the superclass does. A little bit better? Okay. Put this to the side again. Here's a C++ example now. I'm happy that somebody just picked segmentation fault right away. That's the right answer. This is a tight race. Okay. Let's step through this. So we've got these two classes. We've got super and less super. They're named the same way as they are in Java, partly just to try and keep this relationship the same across these examples. They both have this string called item. So we have these two variables that are shadowed. So the superclass is shadowing the subclass. We've got constructors that are using an initializer here, and they're passing instances of string to each of their constructors. And then on line 16 is where our magic starts to happen. So we've got a pointer to super, and that's the static type that's been assigned to S. We're creating an instance of this class less super. When we print this out, S arrow item is referring to the static type of S, which is super. New types may not be defined. Oh, I forgot semicolons. And we get super. So shadowing here, the same rules apply. The same rules apply that did in Java. When we had this two classes, child and parent, here, that value variable was shadowed across those two classes. The value that got printed out in our main method was related to the static type that the variable had. The same thing is true in C++. So we're referring to the static type that the variable has when we're referring to that shadowed variable. So the same rules are applying here as they were in Java. Okay with that? Okay? Okay. Okay. Let me just move that down. Okay. Let's give it a try. Let's give this a try. What have I done wrong? Scroll up, scroll way, way up. Oh, you know what the problem is? Of course, it's not going to work. This print method just returns void. Is trying to print void. That's all of us right now. SpongeBob is our spirit animal. We get super. This is all of us right now. This is all of us right now. So the rules that we had for shadowing, let's go back to this one. The rules that we have for shadowing with instance variables in C++ are the same as they are in Java. We're referring to the static type of the variable. That's what's getting us the value that we're expecting, or that's what's getting us the value that's printed out. The static type of our variable s here is of pointer to super. So when we refer to a shadowed instance variable, we're getting that instance of it from the superclass. In C++, methods can also be shadowed. Methods can also be shadowed. And what that means is that when we refer to the static type of s here as super, a pointer to super, even though it's an instance of less super, the method that actually gets invoked is the one on the superclass itself. So we've not got polymorphism here. We're not calling print on the type that it has at runtime. We're calling print on the type that it has at compile time, the static type of that variable. Because we're calling print in the superclass, we're printing out the value of item that the superclass has, not what the subclass has. This is a part of C++ being different from Java significantly in that you can turn this off. You can turn polymorphism off. You can't do that in Java. If we ran this same example in Java, it would be the subclass's print that we have invoked. But because we're doing this in C++, the methods can be shadowed. So we're using the static type here. Okay. Here's the last example that I've got. Okay. It's less super. We did it. Okay, good. Yes. Here, we're getting less super because in the superclass, we said, hey, it's okay to override this. I would like polymorphism turned on for this method, please. Shadowing should not apply here anymore. In the subclass, I'm saying, I'm going to override that method that's allowed to be overridden in the superclass. When I call the method on this pointer to super, I am now calling the polymorphic method, so the subtype's super. I'll put all these code samples up so you have copies of them. I won't explain them. I'll let you run them yourself, but the explanation is it's here. It's here. Okay, good. Excellent. So the main difference between 6 and 5 here is that in 5, we are not marking our method print as virtual, and we're not trying to override it in the subclass. They are just coincidentally the same name, and we're using the static type when we call the method. In 6 here, we're explicitly marking it as virtual, and we're explicitly saying, I'd like to override this, please. So we get polymorphic behavior on these two methods. All right. Okay, this is enough mind-bending polymorphism, shadowing, instance variable methods in C and C++ and Java. Let's quickly run through this, and then what I really, really want to get to today is destructors in C++. So we've now got overriding methods. We have polymorphic behavior. We have shadowing of methods and instance variables. We have this idea of covariance and contravariance in terms of the way that methods that have the same name and related types are referred to and described. And then we have this idea of nonvariance in Java, where Java having methods that have similar types, even if they are related hierarchically as parameters, they're just different methods. They're not going to be referred to polymorphically. Refinement is one of the last ways that we can think about replacing behavior in a subclass, replacing the behavior defined in a superclass in a subclass. The behavior here is that we've got a superclass and we've got a subclass. And the one thing that the subclass does with relation to its superclass is it calls the same method in the superclass. In Java, this is that super keyword. So here we've got super and subclass. We've got this hierarchical relationship. We have a print method that's being applied polymorphically. The print method in subclass, we would say, refines the behavior of the superclass because it calls that behavior and then it does more stuff. So it's doing something in addition to what the superclass was doing. In C++, if we've got a setup that looks similar to this, so we have a class A and we have a class B. Class B extends class A and we've got this print method. There isn't a super keyword in C++. There's no super keyword in C++. In Java, there is exactly one parent class. There's one parent class. That is the superclass. That's it. So we can uniquely refer to the parent class as super. In C++, we have that multiple inheritance idea. We can have multiple different parents to this one class. So when we're making references to the superclass in C++, we have to explicitly refer to which parent we want to refer to. The superconstructor syntax is similar to the initializer syntax that we saw, so like colon and then a list of comma-separated values. And the super method syntax is similar to method definition. So if I've got a constructor for B, and I want to call the superconstructor for A, after a colon, so I do the method definition for my constructor. After the colon, I would say A, and then parenthesis, and then any arguments that I want to pass to that. This is calling the superconstructor in C++. If I've got this method print in B here, and I want to call the print method in A, then I would use similar syntax to what I have when I am defining the method itself. So I'd use that A and then colon, colon, the class name, colon, colon, and then the name of the method that I actually want to invoke. I don't have any examples of this. I think it's straightforward. It's because it's the same idea that you've done in Java before, but just with slightly different syntax. Okay. All right. Okay. So now this is what I really want to get to today. Orthodox Canonical Class Form, and I will henceforth just call this OCCF because saying Orthodox Canonical Class Form is a mouthful. OCCF is a fairly fancy academic way of saying that we have classes in C++, and as a developer, I want to be able to expect that all classes in C++ have similar behavior to other classes in C++. The behaviors that are defined here are not like print and not like, accessors and mutators and that sort of thing, but the way that we as programmers would interact with classes themselves. There are 4 methods that every class in C++ should have, and if we do not define them ourselves, then our compiler will define them for us. The first is a null or a nullary constructor. This is stuff we've done before. This is that constructor that takes no arguments. There's a destructor. This is a method that's used for the destruction of an object. So we've got a class that's being destroyed because it's going out of scope or because we're explicitly deleting it. This is the method that gets invoked when that happens. There's a copy constructor. You might have done something like this in 1020. You might have done something like this in 1020, where you take an instance of an object and you just copy all of its properties to the one that you're creating. Maybe you did this, maybe you didn't. Not really that important. We will look at it in C++. And then an assignment operator. An assignment operator here, what this literally means is we're going to define a method that is basically called equals, like the equal sign, the assignment operator. And this is the method that will be invoked when we make an assignment to this class type. So if we actually have a statement of x equals y, we're defining which method is going to be called when that happens. This is the only one we're going to do today. We're only going to do destructor today because we need to do it for our assignment. So I want to make sure that we get to that one. The copy constructor and assignment operator we will get to after the reading week break. Here's our null constructor. Enough said. I don't need to say any more about that. In Java, we have this idea of I'm going to acquire resources, and then I can start thinking about what I need to do when those resources are not needed anymore. And the stuff that we really have to care about when we are thinking about that in Java is nothing. It's still nothing. We don't really care at all about this stuff in Java. Just stop asking. In C++, C++ is a language that is a lot more like C in this regard. When we acquire resources, so memory, or we make connections, or we open files, when we do this in C++, we have to care about closing open files. We have to care about that. We have to care about closing open connections that we have to other systems. So if we've got a program that's connecting to a database, we have to close those connections and release those resources to our operating system. Anytime we use that new keyword, so anytime we dynamically allocate memory to create an instance of a new object, we have to correspondingly release the memory that we dynamically allocated, among other things. The destructor in C++ is a method. This is a method that you will add to your class declaration. And the method's name is similar to the constructor, except you put this tilde in front of it. So the constructor is the name of the class, parenthesis. The destructor is tilde, the name of the class, parenthesis. This method will be automatically invoked when you get deleted. So when this pointer is got the delete keyword being used to it, you're trying to explicitly release this. Or alternatively, if you have a stack allocated variable, when that variable goes out of scope, this method will be executed. So if you've got a function, you declare a stack allocated object. At the end of the function, the destructor is called for that object. The purpose of this destructor, is to release resources that we as a class acquired. Destructors in class hierarchies work automatically more than other things do, in the sense that when you have a static type child pointer here, so child is a subtype of parent, when we call delete on this object C later, it's first going to call the destructor on the static type of the thing that we're deleting, and then it will call the destructor of the parent type of the thing that we're deleting. This is working on the static type of the variable that we're operating on. Let's add destructors to two classes that we have. First, I want to add it to Pokemon, and then I want to add it to Trainer. Close this one, and I'm going to take this one, and I'm going to open up Pokemon.h, and I'm going to open up Trainer.h. So Pokemon is this class that we've got that has a private constructor. We don't want to be able to call the constructor outside of us. We want you specifically to call the constructor that takes the name and the type of the Pokemon. We've got these other methods: attack, get nickname, get cure hit points, increase HP. We're going to add a new method here that is the destructor. This shouldn't take any arguments. This is something that's going to get called when this object is deleted or when it goes out of scope if it's a stack allocated variable. I'm going to pop open Pokemon.cpp, and I'm going to go to the very bottom here. Actually, I'm going to define this right next to where the constructors are defined. So I'm going to say Pokemon, the name of the class, 2 colons, then the name of the method. The name of the method here is tilde, and then the name of the class. So this is my destructor. It takes no arguments. And what we should do in here is release resources that we own or acquired in this class. This class has not taken ownership of anything. It hasn't taken ownership of anything. There are no resources that we've acquired. There were no pointers passed to us that we are going to say to the caller, you don't have to worry about this anymore. The destructor that I have for Pokemon is just empty. There's nothing to release. I have defined it, I've declared it, but there's nothing going on inside of it because I don't own anything in this class and I haven't acquired any resources in this class. Yes. So if you are relying on the default destructor, the one that just gets created by the compiler and by the language, it's going to look like that. Thank you for that question. That was good. I am going to add now a destructor for trainer. This one is going to be more interesting. Tilde, the name of the class, declared this destructor as a public destructor. This one is going to be more interesting because the list or the array of Pokemon that I have here, when someone adds a Pokemon to a trainer, I want to say this trainer class is taking ownership of this object. You don't call delete on it. I will release it when I am free with it or when I'm finished with it. I will do that release when I'm finished with it. So I'm going to pop open trainer.cpp on this side. And I'm going to add my destructor. So the name of the class, 2 colons, the tilde, and the name of the class again. This is my destructor. And what I'm going to do is release the objects that I own. We've taken ownership . So when somebody calls add Pokemon here, we're basically saying, hey, you don't have to worry about this object anymore. I promise that I will release it when I am finished with it. So please don't release it yourself. I will release it when I'm done. This is going to go through the process of iterating over the Pokemon that we have ownership of and then deleting them. So I'm going to say here for int I is equal to 0, I is less than Pokemon, actually not max Pokemon, I actually want cur Pokemon. And then I'm going to say delete Pokemon at I. So for each Pokemon pointer that I have in this array, I'm going to call its destructor. If I do not do this, if I don't release those resources, this leads to a memory leak. So this is kind of like you calling malloc and then never calling free again. This is like you calling open and then never calling close again. If we do new somewhere and then we pass that pointer off to somebody else, that somebody else is responsible for cleaning up the resources after it has been finished with it. So we're going to go through the process of releasing all of the Pokemon that we have been assigned as part of this operation. This is fine. This is fine. The one thing that's missing from this is that we haven't really looked at what happens when we have destructors in a hierarchical relationship beyond me saying that the static type is used to call super destructors in the hierarchy. I'm going to pop back over here. When we call delete on an object, and that object is in a type hierarchy, it will call the destructor of the super type based on the static type of the variable. The problem is we only go up in the hierarchy. This is not a polymorphic method. If we have a hierarchy of types, parent and child, and we call delete on that statically typed object of parent pointer, it will only call the destructor in the parent class. We have a type hierarchy of potion, and we have a type hierarchy of potion and item. In order to get the behavior that we're expecting, I want to be able to take that variable p and I want to run delete on it. I want it to run the destructor in the class type that it actually is, not just the super type and not just the static type that the variable has. We have to define this then as a virtual destructor in the same way that we had to define other methods as virtual so that we get polymorphic behavior from them. So let's switch back over to item and potion. I'm going to close all of my other files here. Here's item, and here's potion. So I want to add a destructor to this class. I'm going to specifically mark this as a virtual destructor. And I'm marking it virtual so that it is applied polymorphically. I'm marking it as virtual because I want to call constructors on subtypes of this class when I have this item type as a static type to the variable that I'm referring to. Similarly, I need to write a polymorphic, I need to write a destructor here that's going to override that virtual destructor. So I want to say potion, and I want to mark it as override. The destructor is just a method. It has the same rules as the other methods that we've worked with here. So I'm going to add a destructor now for potion.cpp. So I'm going to pop over here. Type, method name, and then the body of this. We haven't acquired any resources in here. The purpose of this is very much for we want to use virtual destructors. I don't really need to delete anything in here. Don't need to delete anything. We haven't taken ownership of anything. Marking it this way as virtual, it will then go through that process of we're calling the destructors in the way that we're expecting them to be called. So the parent destructor is going to be called as we expect it to be called. All right. Okay. We're right on time. We're right on time. Okay, good. You should at this point now be able to describe and define various concepts related to method replacement. Shadowing, polymorphism, overriding, refinement. You should be able to use words like covariance and contravariance to describe the relationship between methods across classes. I'd expect you to be able to define OCCF, Orthodox Canonical Class Form, in terms of being able to tell me what are the 4 methods or the 4 things that you have to have that are part of this definition. And I'd expect you to be able to create destructors in a class hierarchy in C++, including virtual destructors. So being able to have the actual runtime type of a destructor called based on the runtime type and not just the static type. That's it for today. I hope that you all have a great reading week break, and I will see you back here in about a week and a half. Bye, everybody.